Hey guys, I wanted to go over this worksheet with you, and I'm just going to type these answers. If I'd had it printed, I would have used a .cam, but I wanted it done tonight, so this is what we got. When we do calculating heat, we want to show all work, put our answers in sig figs, and have units with all of our answers. And I'm just going to highlight my final answer, right? So how many joules are released when 80 grams of water cools from 97.2 to 22.5? Okay, so I'm going to come down here to the bottom. If I'm staying in the range between the boiling and melting point, if I'm in that liquid stage, right, then I only have to worry about one Q. So I just have to do Q equals MC delta T, right? In this case, my mass is 80 grams. It is water, and we know that the specific heat of water is 4.18 joules per gram degrees Celsius. And then my change in temperature is always final minus initial. So I'm going to do the 22.5 minus the 97.2. And I'll put my units there of degrees Celsius. So in my calculator, all I have to do is multiply all this together. I am going to start with the 22.5 minus the 97.2. That's a negative 74.7 times 4.18 and times those 80 grams. When I look at all my sig figs up here, they all have 3. So I'm going to keep my answer to 3 sig figs. That gives me 32,500 joules. So that would be my answer, and I'm going to highlight that in yellow. Okay. So that's what we've been doing, right? Now then, other questions are new to us. So question 2 says, how many joules of heat is absorbed to melt 80 grams of ice, knowing that the heat of fusion is 334 joules per gram? So I'm going to use this formula, Q equals M delta H of fusion. So if Q equals M delta H, and I'm just going to put an F to mean fusion, okay? Then I need the mass, which is 80 grams, times my delta heat of fusion, also called enthalpy of fusion, if you ever hear those terms. And that's all I have to do. It's absorbing heat. I don't have to worry about my signs being changed. And so this will just be, to 3 sig figs again, 26,700 joules. Highlighted. My next question says how many joules of heat are released? Oh goodness, right? So I need to pay attention to that word right there. When 15.5 grams of steam condenses, okay? So even though my heat of vaporization is 2,264, if I go in reverse, that means that heat is being released and I need to flip my sign. So I'm going to use my formula, Q equals mass times delta H of vaporization. My mass is 15.5 grams, but my heat of vaporization is going to be a negative 2,264 joules per gram. But simply, I just have to multiply those together. So 15.5 times 2,000, negative 2,264 gives me a negative 35,000 joules. I need 3 sig figs here. And so to get 3 sig figs, I'm going to have to put this in scientific notation by putting that 0 there and then hitting the times 10 to the 4th. joules, I can get my third sig fig that I need, since I had 3 sig figs in my mass. Okay. Number 4 says when I have 34,700, sometimes textbooks will do this too. They'll put a space. That's not two different numbers. That is just a way to, instead of putting a comma, they will put a space there. So that's 34,700 joules of heat are applied to a 350 gram sample of liquid methanol. What must its heat of vaporization be to convert it all to gas? So if I want to convert this to gas, then I need to use Q equals M delta H of vaporization. But this time I want to solve for the heat of vaporization. So I'm going to rearrange my equation. By dividing by mass, I can then find the heat of vaporization. Therefore, all I have to do here is to find my heat of vaporization. I just take my 34,700 joules and divide it by my 350 gram sample. Just like we did in lab, 34,700 divided by 350 gives me a heat of vaporization of 99. 350 is only 2 sig figs, and so that's all I need in my answer. All right. I just copied and pasted our notes that we took. So drawing the heating curve and labeling all the parts, there's an image of that. Okay. However, the second page of this worksheet is much more difficult than the first side, okay? And the reason it's more difficult is because now we're heating up a curve. So I need to know how many places and how many Qs are needed for this to happen. So using the heating curve for an unknown substance, solve the following problems if you have 50 grams of the unknown. There's a list of specific heats and the heat of fusion and heat of vaporization for this unknown substance. So again, step 1, what I would do is I would make sure you're on the graph, you look at where you're starting and where you're ending and how many steps that requires. So our first question says how much heat energy is absorbed by the substance as it goes from 30 to 90. So if I start here at 30 degrees, we are starting in the solid phase. I'm going to have to heat that solid up to 50, okay, not to 90. I have to heat it to 50, then I have to melt it using heat of fusion, and then heat that liquid to 90. So that is a 1, 2, 3 step process. I'm going to have 3 different Qs. So my first Q is to warm the solid. Whenever I have a temperature change, I'm going to use Q equals MC delta T. So the mass they told me to use was 50 grams. The specific heat is when I'm in the solid phase. So I'm going to go to my table, I'm going to look for my specific heats, and in the solid phase, I'm going to use 1.76 joules per gram degree Celsius. And the delta T is, I'm starting at 30, and I'm going to heat it up till it melts, starts melting at 50. So this is going to be a 50 minus 30 degrees Celsius change in temperature. Okay. 50 times 1.76 times, I know that changes, 20 degrees. It still has 3 sig figs in it because it has a 0.0. And so with those 3 sig figs, we have 1,760 joules. However, I am not done, right? The second thing I've got to do is melt the solid to a liquid. To melt, I have to use Q equals M delta H of fusion. The mass doesn't change. Now I have to look up my heat of fusion. That's 555.8 joules per gram. So all I have to do is multiply those two numbers together. 50 times 555.8 is 27,790. I have 4 sig figs in my mass and 4 sig figs in my heat of fusion. And so that's my joules in 4 sig figs. My last step is then to heat the liquid to my final 90 degrees, right? Because I'm still in the liquid phase here. So Q, I'm changing the temperature. I'm heating it up. So that's Q equals MCAT. I still have 50 grams, but now I'm in the liquid phase as I heat this up to 90. So I'm going to come and use that specific heat. Then I'm going to do my change in temperature. I'm ending at 90. I started not at 30. When was it a liquid? So it was a liquid from 50 to 90, right? So I got to make sure that I do that correctly. Right, 90 minus 50 is 40. I'm going to multiply that times 2.08. And multiply it times my 50 grams. And that gives me, again, that temperature is in 3 sig figs, 4,160 joules. Then at the very end, when I've done all of these things, right, I am then going to add my 3 Q's together, 1,760 plus 27,790 plus 4,160 gives me a total heat that the substance absorbs as 33,710 joules. I'm going to be honest, I'm not going to take sig figs off for this. Right? Okay. Now number 2 says how much energy is released as the substance freezes. So if I'm just freezing, I'm just using the heat of fusion, this is just a one step. To freeze the substance, Q equals mass times the heat of fusion. And so, since it's the same mass on this whole page, I'm still going to use my heat of fusion, but I'm freezing it, so that makes it a negative change, joules per gram. And so I'll get a negative 27,790 joules. Since we already did it in the first question, I'm not going to spend time doing that much longer than that. Done. Okay. For question number 3, it says how much heat energy is absorbed as the substance goes from 40 to 120. So at 40 degrees, it's in a solid state. Heating it to 50, melting it, heating it to 110, vaporizing it, and then getting to 120. So that is a 1, 2, 3, 4, 5 Qs for number 3. And the problems don't get longer than this one, right? So this is the longest kind. So I'm going to, step 1, warm the solid. That gives me a Q equals MCAT. So I'm going to use my 50 grams times the specific heat when it is a solid. That is 1.76 joules per gram degrees Celsius. And my change in temperature, I'm starting at 40. When does it stop being a solid? So 40 goes up to 50, right? So that would be a 50 minus 40 change in temperature. So now 50 times 1.76 times the change in temperature of 10 is 880 joules. In the second part, I then have to melt the solid. In melting the solid, I have to use Q equals M times the delta H of fusion. So 50 grams times the delta H of fusion, right, was that 555.8 joules per gram. And so that will be the same 27,790 joules. Then I have to warm the liquid. When I'm warming that liquid, I'm changing its temperature, so that means I'm going to use MCAT. 50 grams. Now I'm in the liquid phase, so my specific heat of the liquid was 2.08 joules per gram degrees Celsius. And I'm going to warm it completely. So as I warm it completely, I went from 50 is when it started being liquid, and I'm going to warm it all the way up to 110. Okay, so 110 minus 50 will be my change in temperature as it's in that liquid phase. That gives me a total heat absorbed as 6,240 joules. Step 4. If I don't put the decimal, maybe it'll be fine. I then need to vaporize or boil. Vaporizing that liquid to gas. So it's melting the solid to liquid. In vaporization, I'm going to use Q equals mass times the delta H of vaporization. So 50 grams times the heat of vaporization was 1993.2 joules per gram. So by multiplying 50 times 1993.2, you get 99,660 joules. Then the last step, because this one takes the longest, is then to use heat up the gas. We're going to change the temperature of that gas, so MC delta T. This time, the specific heat of the gas is 1.34 joules per gram degree Celsius. And the change in temperature, the question asked for us to stop at 120. So we had vaporized at 110, now we're just going up 10 more degrees. So my change in temperature would be the 120 minus the 110. Another 10 degree change. 50 times 1.34 times that 10-degree change is 760 joules. And as much fun as that was, we then get to add all of those together. So when we add 670 plus 99,660 plus 6,240 plus 27,790 plus 880, we get a total heat of 135,240 joules. Whew, that's a lot. So you see why sometimes we put answers in kilojoules, because 135 kilojoules just doesn't seem so bad, right? As a number to write down. Okay, so that was question 3, and that's the longest kind of question. The last question is question number 4, and it says how much heat is released. Oh, released is a key word, right? We're thinking negatives here. As the substance condenses at 110 and continues to cool to 60. Okay, so we're going to condense the gas and then go to 60. That's only 2 steps. Okay. So then I'm going to use a Q equals M delta H of vaporization, because condensation and vaporization happen at the same rate, the same joules, the same amount of heat it would require. That was the 1993.2 joules per gram, which we are condensing, so we got to flip the sign and make it negative 99,600 joules. And then we also needed to cool it all the way down to 60. So since we're going to change the temperature, that's an MC delta T. And that's going to give me my mass. The specific heat is after we've condensed it, we are in the liquid phase, so that's the 2.08 joules per gram degrees Celsius. And my change in temperature, I'm ending at 60, but I started at that 110. So now all my units cancel. I'm left with joules. 50 times 2.08 times that change in temperature will give me a negative 5,200 joules. So then to add those together, gives me a negative 104,860 joules. Okay, so I worked out all those problems. Now there is a Canvas quiz for you to try.